one. So I'm going to start recording, and what we're going to talk about today is we're actually going to be doing a lesson straight from Canvas so that you don't have to take notes on it. And I literally included every detail from Canvas. We're going to go through, there is some math. It's not as hard as the dimensional analysis math. It's much simpler. So we're going to talk about how to do the math and do a couple examples, and then you will be ready to take a quiz in Canvas. So we are talking about weighted isotopes. If you have already gone through this lesson, I excused Janie Mae from this because she actually got 100 on the quiz and really clearly showed me that she knew how to do this, right? So I didn't want her to come to this session. And likewise, if you guys do similar things in the future, like you get 100 on something that we're going to talk about, then I will tell you when you don't have to come to the session. So first of all, I wanted to add a reminder, which I meant to add actually to the slide, and I didn't. Let's see. Come on, Google Slides. Oh, really? Okay. So next week on October 13th, there is no school. So no school, that means no virtual session. So next week, if you try to log on, we won't be having a session. So please don't email me about it because we're not having one. So our objectives for today are going to be to identify the structural differences between the isotopes of elements and determine the weighted average mass of an element when given the appropriate data. So the math part, like I said, is less scary than dimensional analysis, but still it's math, so we're going to go through it step by step. And the structural differences part is pretty easy. For some of you guys, that might be a review. So we're going to start off with this warm-up question. It's going to help us get mentally ready, but also give us some information that we're going to need in order to answer this. So what are the parts of an atom? There's three main parts. You don't need to go like subatomic particles here. And then how can we use the periodic table to identify those parts? So take a second to think about those. And if you want to pop your answers into the chat so we can start kind of putting this information together. Anyone have ideas on the parts of an atom? I'll give you the letters that they start with. Thank you, Abby. Protons, neutrons, and electrons. That's not how you spell neutron, is it? There we go. Electrons. All right, awesome. So, thank you, Chris, also saying the same thing here, protons, neutrons, electrons. So those are the three main parts, right? Just to make sure we know exactly what is going on in those parts. Keep in mind that protons, are positive, right? They're located in the nucleus of the atom. Neutrons are neutral. Sometimes that's written as one of those zeros with a slash through it. They are also located in the nucleus. And then electrons are negative, and they are located on the outside of the atom, right? Sometimes it's referred to as an electron cloud, but not always. Hopefully you have a picture of this in your mind or drawn in your notes. So then the next question is, how can we get this information from the periodic table? So on the periodic table, we usually have a box, right? And we have our element inside, and Chris is giving us some awesome information here. The atomic number and the atomic mass are going to be able to tell us pretty much everything that we could want to know about these things, right? So if we're going to talk about carbon as an example, carbon has an atomic number of 6, and carbon has an atomic mass of 12.01, something like that, 12, we'll say, right? And then we would also, in theory, have our carbon symbol. It's really hard to draw with the mouse. And what we can actually learn from these numbers is, what does that 6 tell us? Thank you, Abby. It tells us the proton number, right? It also tells us the electron number in a neutral atom. We have a neutral atom, that means we need to have an equal number of positive and negative charges. So unless it tells you that the atom is charged, we know that this will equal actually protons and the electrons number. So that means that carbon has 6 protons and 6 electrons, right? If it was charged, which is rare, carbon is not usually charged, then we might see 7 electrons, right? If it was a negative charge, we might see 5 electrons if it was positively charged. So just thinking about adding up those positive and negatives together. Then what about the atomic number? What does that tell us? It tells us the mass of the nucleus, which in our case is going to be protons plus neutrons. So with some simple subtraction, we could figure out the number of neutrons in a carbon atom. We round our atomic mass to 12. We can subtract out our number of protons, which is 6, and we end up getting 6 neutrons. And that is correct, that carbon is 666, which is crazy. It's also the basis for all life. Pretty weird. If you believe in the Illuminati, very strong argument there. So we basically can get this information from the periodic table. Today, what we're going to do is talk about this number and how they get these weird decimals, right? Because we think, well, if it has 6 neutrons, then why isn't it just 12, right? And also, we're going to talk about different isotopes or different variations of an element. So I have to erase each one of these things one at a time, so this will take a second. There we go. So examples of isotopes, right? Just because really we want to be thinking about, well, why do we even care about isotopes? Well, they're actually used in a bunch of different science, especially in research, right? So here's an example of them being used in archaeology and geology. So the question really that scientists were asking is, okay, if dinosaurs were killed by a meteor, then we need 2 things. 1, where's the crater? And 2, is there any other evidence that is supporting that a meteor possibly hit Earth around the time that they went extinct? Well, guess what? There is, actually. So first of all, they did find the crater. They used gravity to find that the crater is located right next to the Yucatan Peninsula in Mexico, right? Almost impossible to see, but they could actually tell from gravity levels that there was a hole there from where a meteor had hit. And then they thought, okay, that's pretty compelling. But of course, because we're scientists, right, other scientists were like, nah, you're crazy. That's not what happened. So people started looking for layers of different elements that are found mostly in meteors and asteroids. So the big extinction that knocked out the dinosaurs, right, occurred between the Cretaceous and the Paleogene time periods in the geologic time scale. So scientists started going back into the rock to how old that was and looking for clues. And they actually found an iridium layer, which is this black layer that you see in this picture. So a normal person looking at this rock would just be like, cool, there's a black layer in it, right? Scientists knew that that was iridium, and that iridium comes in high concentrations in meteors and asteroids. So that's just more evidence to support that possibly it's possible that a meteor killed the dinosaurs, which a lot of people still disagree with, but I would say most scientists are saying that it's true, especially after this iridium layer was found. Another use, right? Radioactive medicine. So a lot of times if you're having problems with certain organs, especially surprisingly the heart or liver, scientists, in this case doctors, will actually have you drink a radioactive isotope, which is not harmful to you. I put that in quotation marks because it's radioactive. Of course it's harmful, right? But you're drinking such a small amount that the risk is, the benefits outweigh the risk. In this case, being able to look at your organ and see what it's doing is more important than the tiny amount of radioactivity that you might be exposed to, right? Same concept with an X-ray, right? X-rays are super damaging. They can cause cancer. However, if you have a broken bone, it's important to use an X-ray so they can identify the broken bone so that you can heal. So it's a similar concept, but then what ends up happening is doctors can get imagery kind of like this person that we see over here. This is the stomach, right, where that radioactive isotope was probably drank, and they put you in like a CAT scan, and they can actually follow it going down the esophagus into the stomach, and they can see what's going on. Another use, this is probably the most well-known, I'm having a hard time speaking today, well-known use is radioactive dating. And you might have learned about this in previous science classes or heard of it before. I don't know where to put the videos so that they're not in the way. I guess they're always in the way. But we use carbon-14, which we'll talk about what that means in a second. But essentially, these radioactive isotopes, they decompose at a certain rate. So if we can see how much is there in a rock or a fossil, right, or any kind of bone, we can actually tell how old that rock is or that organism, right? So they use this to date specifically rocks, but they can also actually use this if remains are found and they want to find out like when that person was maybe killed or died, right? They can actually use carbon-14 and they can predict pretty much down to, I wouldn't say the day, they might be able to go that far, but they can predict within a pretty good amount of time how long ago that was or how old that organism is. Pretty cool stuff. So naming isotopes, this is straight from Canvas and is pretty self-explanatory, but when we're talking about an isotope, you will see a number with it, right? So if it just says carbon, we're assuming that we're talking about the most abundant form of carbon, which is carbon that has an atomic mass of 12, right? Or whatever the atomic mass is on the periodic table usually. If we see carbon-14 or we see a superscript 14 with a C or with a carbon, then that is actually telling us that we're talking about an isotope, right? And an isotope is going to have a different atomic mass than a regular carbon atom. So we know that protons and neutrons equals the atomic mass. So what do you guys think is changing in an isotope? Are we changing the protons? Are we changing the neutrons? Are we changing both? If we're changing the mass, which one are we changing? Or both? Abby says neutrons. If you agree with Abby, could you put a 1 in the chat? Oh, Jonathan says maybe it's both. Anyone else agreeing, disagreeing with Abby? All right, so to ask you a question, Jonathan, if we change the protons, we're actually going to change the element, right? Because remember, our atomic number, or the number of protons actually determines which element it is. So we cannot change the protons. So protons equals that element. That cannot change, otherwise we're going to be a different element. The neutrons are going to be the only thing that we can change here, because that will change the atomic mass without changing the element. So for example, with carbon, right? Carbon has 6 protons. If we take a proton away, then we have boron, right? 5 protons equals boron. Well, we don't want to do that, right? If we add a proton, same thing, we're going to change the element. So our mass is changing. And what that means is that for carbon, at least, we always have 6 protons. That's not going to change. But for carbon, you can see 6 protons, you can see 7 protons, or excuse me, I'm saying the wrong stuff here, guys. Neutrons, thank you. 7 neutrons, 8 neutrons, right? In theory, there could be, 1,000 different ones. Most elements have 2 to 4 naturally occurring isotopes. And I say naturally occurring because that means they exist in nature, right? We could create a carbon that had 40 neutrons if we wanted in a lab. There would really be no purpose to do that except to say, cool, we made a carbon with 40 neutrons. But when we see that atomic mass written after something, so before we saw carbon 14, right, what that is telling us is that there are 6 protons, because there's always 6 protons, so how many neutrons are we going to have in a carbon 14 isotope? Thank you, Zach. 8. We're going to have 8 neutrons in carbon 14, right? If we saw carbon 13, we would have 7 neutrons. So all you have to do is take that mass number and subtract the protons. They probably won't tell you the protons. You'll have to look on a periodic table in order to see them. So now we're going to get into the math. So we're going to identify the number of protons and neutrons of these isotopes. You're going to need to use a periodic table. So you can just Google periodic table. I will post a link in the chat of one that I usually use. Which honestly, you should probably have a periodic table bookmarked or printed, because we are going to use it pretty frequently. Notice on this periodic table that our atomic number is in the upper left corner, and our atomic mass is on the bottom, right where we would expect to see it. I clearly cannot circle well there, but you get the idea, right? So just in case you couldn't see where the atomic number was. So going back to the question here, we are trying to find out the number of protons and neutrons in hydrogen 3, carbon 13, and uranium 235. So I'm going to give you guys 2 minutes to do this. Should be enough time. I was trying to see if I have a periodic table in one of my books, but I don't think so. They're all biology books. So this is the easiest part of the math, by the way, but an important step, just being able to identify proton and neutron amounts. We're going to go through it step by step in 1 second, Chris. All right, sorry guys, I was checking out the periodic table so I can make sure I knew the answers to these. So we want to find our protons, neutrons for each of these 3 different isotopes. So the first step that we should do, hopefully you tried to do this on your own, is we should actually be thinking about, no, sorry, I'm having Zoom issues. It's not letting me click in my box. All right, we should be thinking about the number of protons first, because that's going to be the key. So how many protons does hydrogen have? 1, right? Where did we find that? All we did was look on the periodic table, add hydrogen, and we see that its atomic number is 1, so it must have 1 proton. Okay, that was the easy part. Next step is neutrons. Well, in order to figure out how many neutrons we have, we're given our atomic mass of our isotope right here. We know that our atomic mass equals protons plus neutrons. So we're going to say that we have an atomic mass of 3. We want to find out neutrons. We're going to subtract our protons to get our neutrons, which is going to be 2 neutrons. Right? So to find those neutrons, what you're going to need to do is subtract the proton number from the atomic mass. You might want to have that written out in words. So atomic mass minus protons equals neutrons. So in this case, our atomic mass is always going to be given to us in our isotope. Okay, what about I was trying to move this over so I have more space. Okay, so what about for carbon 13? This one I kind of gave away earlier, but we have 6 protons in carbon, right, which we could go to the periodic table to confirm, and it does have an atomic number of 6. Neutrons, right, we're seeing here that we have 13 as our atomic mass. We're going to subtract our protons to get 7 neutrons. Okay, and now uranium 235. By the way, these are actual real isotopes here that do exist or can exist in nature. How many protons does uranium have? It took me like 2 minutes to find this on the periodic table, in case you were struggling. Thank you, Abby. 92 protons, right? So uranium is number 92. So then to find our neutrons, we're going to take the atomic mass that they give us, 235. We're going to subtract our protons, and we get what? 143. Okay, so that's the first part of the math here, is being able to find the protons on the periodic table and then do some subtraction to calculate the neutrons. Type a 1 in the chat if you feel like, okay, I understand that, I think I could do that. Type a 2 if you want me to do another example. Okay, I'm seeing mostly ones and I see 1, 2. So we're going to do one more. So let me take a little glance here at the periodic table. Let's try Neptunium, which is abbreviated as NP, 245. So Neptunium 245. Probably not a real isotope, I just made it up. And let's also try iodine 130. So our first step is to find these guys on the periodic table. Neptunium happens to be right here next to uranium, number 93. And we see it's really tiny mass there, which we don't even need really because we are told what our mass is here. So we know that our number of protons for neptunium is 93. Right, all I did was find its number on the periodic table. And then in order to find our neutrons, we're going to take our atomic mass, which is given to us as 245. We're going to subtract, I'll make this an equal sign so it's a little easier. We're going to subtract our number of protons, and we're going to find out how many neutrons do we have. – 152 neutrons. Okay, now that's a lot of neutrons. And then what about for iodine? For iodine, what is our atomic number or our number of protons? (53), right? We got that straight from the table here. Upper left corner of iodine is telling us 53. So we know that our proton number is 53. And then to find our neutrons, we're going to take our mass, which is given here as 130, subtract out our protons, and we get how many neutrons? 77. Okay, so you can do this as long as you have a periodic table, or you're given the information of how many protons there are, right? And an atomic mass, you could always find the neutrons. Okay, so we're going to move on to make the math a little harder. If you're still feeling stuck on this, I would recommend looking at the periodic table and looking at different elements and actually trying to come up with your own question to answer, like I just did right there. So, how could this math get harder? Well, how could it not? The next part is, okay, how do they get the mass on the periodic table, right? It's 12 point something for carbon, right? All of them you see a decimal. And if you know that that is the protons and neutrons added, you should know there shouldn't be a decimal, right? Since when do neutrons come with extra mass? They don't. So what this is a weighted average of all the different isotopes that exist, and it's weighted by their percentage. So for example, I did carbon here and then I put oxygen here, but actually maybe I'll replace that with an oxygen. That's a good idea. Oops. So you guys can see my process here. It's so complicated. So what we're going to do is actually do some multiplication of percentages here in order to find out our weighted average. And if we look at oxygen, we notice that oxygen 16, which has a mass of 6, this is like the unit for atomic mass, is 99.762% of the oxygen that exists. Oxygen 17 and 18 are two isotopes that naturally occur. However, tiny, tiny percentages, less than 1% together, right? So when we look at this data as a start, what we should be thinking is, well, the atomic mass is probably going to be pretty close to 16 because that's what most of the oxygen is. And when we look at the periodic table, what do we see? It's 15.99999. Okay, so how do we figure that out, right? We could round this to 16, by the way. How do we figure that out? Well, we need to take our percent and we need to convert it into a decimal, which for some of us that might be easy and some of us might be like, how do you do that, right? Anytime we have a percent, let's say we have 90%, as a decimal, that is the same thing as saying 0.9. Right? If we have 0.02%, that is the same thing, as saying 0.0002. So what did I do? To take a percent and go to a decimal, you can divide by 100 or shortcut, which you guys know I love shortcuts. You can move the decimal 2 places to the left and add zeros. So if we take 90 and we want to make it into a decimal and we're doing the shortcut, we get rid of that percent sign because we don't need that. Oops, I thought it would just let me write in a different color, but apparently not. Okay. There we go. So we're going to put our decimal at the end of our number, and we're going to move it 2 places to the left. So 1, 2, and then put our decimal there, and we end up getting 0.90. Same thing here. We moved it 2 places to the left, and we had to add zeros. Hopefully your handwriting looks better than my digital handwriting. And we get 0.0002. Right, so this is the most important and confusing step. If the decimal thing is like, what is that? Just divide by 100. If you divide 90 by 100, you will get 0.9. If you divide 0.02 by 100, you will get 0.0002. Right, so you can either divide by 100 or move the decimal. I personally like moving the decimal because I think it's easier. And I did not mean to erase that already, but it will be in the recording. So in order to do this for oxygen, right, all we're going to do is take our mass and multiply it by the percent as a decimal and then add them all up. So we see that for a mass of 16, they moved the decimal 2 places to the left. We're going to multiply by 0.99762. For 17 atomic mass units, we're going to multiply by 0.00038. Right? They moved the decimal 2 places to the left. And then same thing for atomic mass of 18, so that we end up getting an average of 16, right? And this is an average based on percentage. So you could do this exact same kind of math if you were, let's say you knew like there were 3 types of something going on and 90% was this and 5% was this and 5% was this. You could do the same math to find the weighted average. But that's how they found these averages on the periodic table. They might be slightly different on the periodic table because they might have included other isotopes here that we don't know about that aren't listed, right, that have lower amounts. Obviously, the periodic table is going to be the most accurate. What we do might be less accurate, which is fine. So let's do an example. We're going to do one example together. You guys are going to do one example, and then there is going to be an exit ticket example as well. So copper has 2 naturally occurring isotopes. Copper 63 with an atomic mass of 62.94, right? They rounded it in order to not say copper 62.94, makes up 69.17% of the sample. And copper 65 with an atomic mass of 64.93 makes up the other 30.83%. Calculate the weighted average atomic mass of copper based on the given information. Please give your answer in a total of 4 significant figures. Okay. Step 1. Let's list out what we know, right? We know that the copper with a 62.92 atomic mass is 69.17%. And we know that our copper with a mass of 64.93 makes up 30.83%. Okay, so based on what we just looked at before, what do you guys think the first step is going to be? Great, thank you, Abby. Make the percents into a decimal. So in order to do that, we're going to move the decimal 2 places to the left or divide by 100. And for our first one here, we're going to end up to convert that percent into a decimal. We end up getting 0.9717, right? We've gotten rid of the percent, so we don't carry the percent there. And if we do the same thing here, converting that percent into a decimal, we're going to get 0.3083. Okay, next step is going to be to set up our multiplication here. We only have 2, so it's not going to be too much. But what we're going to want is we need to multiply our percent as a decimal by our atomic mass, and then add those 2 together. So the way that you would write that out, right? They used like brackets. You could use parentheses, whatever makes sense to you. But I'll do this in a different color even. I'm trying to like have more fun with Zoom. We're going to say 62.92 times 0.9717. And then we're going to add to that the same thing for our other mass, right? 64.93 times 0.3083. And when we do that math, let's see what we end up getting. Get my calculator out here. And you guys can pop in the chat if you've already calculated this. We can see if we got the same answer. Definitely try to type this into your calculator right now to make sure that we're getting the same answer. What are you guys getting for this one? Okay, Jonathan's provided an answer. Let's see if we get people agreeing, disagreeing. Making sure I did this correctly. Okay, I got the exact same thing as you, Jonathan, and actually we have to add those two together, right, in order to get our average masses. Now, what's interesting about that is if we have 61.129364 plus 20.017919, we actually get a pretty high mass here, right? We get 81 point. They asked us to have 4 significant figures, so we only want to have 2 places here. So, let's see, 0.12, 81.13. And that seems strange that it's so much higher than the ones given here, right? But that is the correct math. Unless I'm missing something here and you guys are seeing something I'm not seeing, but that's what I got. So let's try another example. You guys are going to try this one, and then we'll go over it. So here are the isotopes. 3 isotopes of argon occur in nature: argon 36, argon 38, and argon 40. So calculate the weighted average atomic mass of argon, giving your answer in a total of 5 significant figures. So go ahead and do the same steps that we did before. Start with what you know, convert those percentages into a decimal, and then do your multiplying and adding. So we're going to spend probably like 2 minutes working on this one, and then we will come back and see what we got. All right, I'm going to start writing out what I did. And our first step was to write what we know. So 35.968 is one of our argons, right? And that makes up 0.337% of a sample. We also have argon 38, which is 37.963. That makes up 0.063% of the sample. And then we have argon 40, which is 39.962. And that makes up 99.6%. Okay, so that was the first step, write out what we know. Second step is going to be to convert our decimals, or excuse me, our percents into a decimal. So our first one, to convert that to a decimal, we're just going to move our place, or decimal, I can't even speak, move our decimal 2 places to the left or divide by 100, and we should get 0.00337. For our second one, we already have a 0 in front. We're adding 2 zeros because we're moving 2 places to the left, 0.00063. And then our last one, 99.6, moving that decimal 2 places to the left, we get 0.996. Okay. The next step is to set this up and multiply. So our first atomic mass is 35.968. We're going to multiply that by its abundance as a decimal, which is 0.00337. We're going to add to that our second atomic mass, which is 37.963 times 0.00063. A lot of 6 3s in that one. And finally, we're going to add our last variation here, which is 39.962 times 0.996. So basically, all you're doing to set up this in sorts, it's a way to basically have an equation for this. All you're doing is multiplying the percent as a decimal times the atomic mass that's given for the isotope. And Chris, if you're still not understanding this, I recommend to you to go on YouTube and search weighted isotopes and watch some more videos about it, or go into the Canvas lesson and see if maybe reading about it helps you kind of understand it a little bit better. So when we do all of that math, what did you guys get? And by the way, 5 significant figures. I just realized I did the wrong thing on the last one. That means we want 5 digits after our decimal, right? Because those are going to be our significant figures. Did anyone else other than me get an answer for this one? Abby got 40.163. I got 39.94734. Which is kind of close to what Zach got. We all got different stuff. Uh-oh. All right, well, we're in the ballpark. So keep in mind, there is a short answer question on the quiz where it's going to ask you to show this work and explain it, right? And if you're slightly off by like tiny amounts, that's fine. It's still going to count as correct. So like Abby and Zach would both have gotten this correct. The answer I got was 39.94734. And again, the unit is that U, the micro symbol, which is atomic mass units. So if you got somewhere between 39 and 40.5-ish, I will say that is great. Otherwise, try that math and see if you get, maybe you had something typed in wrong. Make sure that you've converted your percents to decimals correctly. Okay. So that's the math for these isotope questions. For this last one, you guys are going to turn it in as an exit ticket Oh, and also notice that kind of makes sense, the answers that we got, right? I know on the copper one, it doesn't make sense, the answer that we got, but it is what it is. In this case, 99% of the argon that's naturally occurring has an atomic mass of 39.9. So it makes a lot of sense that we got something very similar to that, right? If we got 80 on this one, that would be a little bit weird. So to get full credit on this, I want you to show your work, even if it's just listing out what you're multiplying, and explain how you did it. You're going to have to do this on the quiz as well. So if you do something and you show your work, I'll be able to actually give you feedback, right? Like if there's one step in particular that you got wrong. So imagine that scientists discover a new element. Yes, that's what I got, Zach. Yes. So imagine that scientists discovered a new element given the symbol X. If 93.7% of the sample is an isotope with a mass of 272.98, and the rest of the sample is an isotope with a mass of 275.96, what is the average atomic mass of the sample? Keep in mind, they didn't give you the percentage on this second mass. You're going to have to subtract 93.7 from 100 to find that percentage. All right, so this is the exit ticket, and it should be showing up on your Canvas calendar now. I had it show up at 10 a.m. So I want you guys to try that, show the math, explain what you're doing, right? If you're still feeling confused about this and you think you're going to spend a little bit more time learning about it before you attempt the exit, that's fine, right? In fact, I would say do not attempt the exit until you feel confident that you know how to do this, okay? And then again, when you take the quiz, right, it's the same kind of process. It's going to ask you to explain how you did it and what your answer is. And then if you don't show your work, I can't really help you because I don't know what you're doing. All right. Otherwise, are there any questions about the class in general? Not necessarily about weighted isotopes. If you do have a specific question about weighted isotopes, like you don't understand one of the steps in particular, include it in your exit slip and I'll be able to answer it there. Otherwise, questions about the class? Okay. Well, if you feel confident that you understand how to identify protons and neutrons and also how to calculate that weighted atomic average, then when you finish the exit slip, you could go straight into the quiz on this topic, right? It's a pretty short quiz. And then otherwise, next week, no virtual session. I will see you guys again on the 20th. Oh, I didn't tell you the code word. The code word, I'm going to type in the chat. It is a living organism, in case you're like, what is that? That's the code word in the chat. Make sure you write that down or save it on your computer so that when you turn in this exit slip, you can include that code word. Chris, you got the code word? Yeah, it does. Good, I'm glad you got it. Okay. Otherwise, guys, I will see you on the 20th.